Alright, welcome to today's lesson again. This is a continuation of what we've been doing. Don't forget what we've been doing. We've been trying to calculate the dimensions for the cross section of our beam. So the last video, in our previous video, we plotted this diagram for the forces that are acting on the beam. So today we'll be plotting the forces, we'll be plotting for the moments that are acting on this diagram. Remember, a moment is basically the bending effect of a force. So the forces that we are having here will start gaining a certain distance. Once they gain this distance, then they'll turn into moments. So yeah, so let's get into things. So again, we'll be using the method of sections to determine here. If I get to my section mx11, let me say mx11, I can see a force here, but this force does not have any bending effect because it has not gained any distance. So my M11 will be equal to 0 kilonewtons per meter. Sorry, this is meter. 0 kilonewtons meter. So my first section here will be equal to 0. Remember, in my previous diagram, in my previous video, I said if a force, if you see a force on the force diagram, it's a rectangle. On the moment diagram, it becomes a triangle. So this is what will happen. We have 0 at the beginning here. Our mx11, the moments at the section 11 is equal to 0. When I get to the moments at 2, sorry, when I get to the section at 2, what happens is that this 21 here gains a certain distance. So I will take this one, this force here, multiplying by this distance will give me the moment at the section number 2. So 21 point what we have there? We have 21.3 is equal to times 1 will give us 21.3 either way. Alright, so here again we get back to where we're going to plot this 21. For us to do this, we look at where this force is being applied from. If it is being applied from under the diagram, from under the beam, then we have what we are calling here N. This is Russian N, which means Nizhny Volokna. Basically in English it will translate to lower fibers. This force is being applied under the beam, so it is affecting the lower fibers. If it is being applied above the beam, it will start affecting the upper fibers. So here we have the Nizhny Volokna, here we have the Verkhny Volokna. So we have the upper and lower fibers. Sorry, fibers here. So we can see that this one is being applied under the beam. This force 21.3 is being applied under the beam. Therefore, I'm going to plot it under the beam. So I'll plot my 21.3 here. Kilonewtons. Sorry, I'm supposed to plot it here. Since we have a 0 here, it will come here. I'll have a triangle. I'm going to have a triangle like this. Dark. I'll have my 21.3. This is not supposed to be here. 21.3 kilonewtons meter. And then I'm going to shade it using a red pen. It's visible. So I'm going to shade it using a red pen. And then I'll move on to my second. I'll move on to the third section. When I get to the third section, I can clearly see that nothing is changing. Even though I can see these 12 kilonewtons. This 12 kilonewtons does not have any distance. It has not covered any distance. So it cannot be turned into a moment. So I'll say my mx1, this is supposed to be 2 is equal to my mx33. This is what we're going to say. And then when I get to my mx44, I can now clearly see that that 12 here has gained a certain distance of 1. So it can be turned into a moment. let me just do this. That 12 can be turned into a moment. So I'll be writing here. This 12 that I have here can now be turned into a moment. Therefore, I can say, remember, this 21.3 has now gained a different distance. At this point, we're applying it at this section 44. So it has gained a distance of 2. So we're going to say at mx44, we have 21.3 times 2. This is Nizhny, it is lower. And then we'll multiply it by 12 Verkhny. So we're going to add it to 12 Verkhny plus 1. So we multiply it by 1. 21.3 times 2. 21.3 times 2. What is happening to my calculator? 21.3 times 2 will give me 46.2. 42.6, sorry. 42.6, and then this will give me 12. This is Nizhny, this is Verkhny. So since we're having one that is lower and the other one that is upper, I'm going to subtract them. I'll say it minus 12. It gives me 30.6 Nizhny. So I'll come to my diagram here and plot this 30.6. Let me put it at this point. So this is basically, this scale is just an approximate scale. Just make sure that 21 looks bigger than, sorry, looks smaller than 30. I have something like this, and then I'll shade this part here. This is how my diagram is coming out so far. But then when I get to my diagram for the forces, I can notice here that this here is crossing the 0 axis for the force. So what I'll do is, at the point where it is crossing 0, I'll draw a certain line. I'll draw a line which will come as far as this. And then I will have to determine the value of z. So z is basically the distance from this point here to where this is crossing the 0 axis. So this will become my z. How do I determine my z? This length. For me to determine this length, it's very easy. What I'll do is, I'll take this 29.7 and say 29.7 minus 13z, because that 13 is acting over a certain it's acting over this length. So per meter, I have 13.5, 13 kilonewtons per meter. So I'll multiply it by this z to find the value of z. I'll equate this to 0, and then I'll say z is therefore equal to 29.7 divided by 13. 29.7 divided by 13 gives me 2.3. This is equal to 2.3 meters. So this is 2.3 meters. Z is equal to 2.3 meters. Having done that, we can now get back to our plotting business. So if this is 2.3, then the distance here, that remains here, or the length that remains here, is 3 minus 2.3, which gives me 0.7 meters. So when we get back to our plotting business, we have another section here that has come up as a result of this. So I'll put another section here just immediately after this point. I have my section 6. My section 6 here, I need to calculate the moments that are occurring in this section of mine. So in order for me to do this, I will say mx66 is equal to, again remember, this 21.3 that we are having here in this case it has now gained a distance from this point to this point. So it will be 2.21.3 times 2.7. This is lower fiber, and then this 12 is equal to 12 times, this is now 1.7. This is upper fiber, which will be also equal to which other force? We now have this shear spread out force, which is 13. So 13 is applied midway of this distance, so I'm going to say 13 multiplied by 7 times 0.7 times 0.7 over 2. Since this 13 is being applied midway here, so we'll find the actual value for the entire length, and then we're multiplying it by halfway of where it is being applied. This 13 is also Vierkni. So we're going to now say 21.3 times 2.7 will give me 57.51, and then I have 12 times 1.7 will give me 20.4. Then I also have 13 times 0.7 times 0.7 divided by 2, which will give me 3.185. Remember, this is Nizhny, this is Vierkni, this is also Vierkni. So I'll add this, keeping in mind that where I'm having this the forces being applied from one direction, I'll add them. If they're being applied from different directions, I'll subtract them. So in this case, I'll add 20.4 plus 3.185 plus 20.4, which is 20. Alright, so we've calculated that at the section 6, the moment is equal to 33.925. That is affecting the lower fibers. So I'll plot this 33. It will be here, 33.9. But then remember, I said if you have a shear spread out force, what this tells us is that on the diagram for the moments, we're going to have a parabola. This parabola opens up to face the direction in which the shear spread force is being applied. So if this, we can see from our equation here that the direction in which this shear spread out force is being applied from is from the upward direction. So our diagram here, our parabola will open up in that direction. So I'm going to have a parabola that will open up like this. It's only that it can't be visible very much here because of the distance. So this is a parabola. It's opening up like this. If I can draw it here, the parabola is opening up like this. It is opening up upwards. And then to get to our final dimension, so to get to our final moment, this is what we can do. To make things easy, I can flip this paper. Remember, we started from this point going this direction, but to make things easy, I can flip it and start from this direction. If I start from this direction, I can clearly see that my moment at the point, at the cross section, 5 is equal to 0, because this, even though we have a force here, this force, it has not gained any distance. So we can easily say mx5 is equal to 0 kilonewtons. So from here, I'll move to 0, and then I can freely plot the diagram now. Freely plot it like this. Since this is a shear spread out force, I'll have something like this. I'll have a parabola that is opening up in the direction of the shear spread out force. And then my pen. And then I will shade this part. So basically, this is how my diagram will look like for the moment. Remember, when plotting this diagram, what we're actually looking for is this one. we're looking for the maximum bending moment. All right, now that we've calculated our maximum bending moment, let me just give a brief explanation what this means. The maximum bending moment basically shows us the exact point at which our beam will start getting deformed. So it is at this point here, just immediately after the cross section 6, where this beam will start getting deformed. It will start bending at this specific point. So basically this is what our M max entails. But then don't forget, our entire job has been to determine the dimensions of the cross section of this beam. So we've been looking for the value of H.